Thank you very much. I'd just like to say I'm timing myself, so you can't take any minutes from me. So, all right. This is a quote that I took off a wildlife photographer's website. As mega herbivores, rhinos are ecosystem engineers and ecological drivers that critically help shape the health of the wilderness so that other species may thrive. And I'm pretty sure that most of us would agree with this statement. We think of rhinos as ecosystem engineers and keystone species, and we understand that because of these three characteristics, they have the potential to disproportionately impact the environment and other species. But what you might not know is that most of what we know about rhino impact is based on very few studies. It's mostly theoretical and based on inference from studies from other species. So this is a meta-analysis on elephant that covers 68 years of elephant impact research. And it reports on 367 peer-reviewed publications that specifically deals with elephants impacting ecosystems. There's no such meta-analysis for rhino because there's only a handful of studies that empirically test the impact of rhino. Okay, but it's not like we know nothing. So what do we think we know about how rhinos are impacting the environment? So one of the most well-known ways is that rhinos are suspected to create and maintain structural heterogeneity within the grass layer. And so direct feeding reduces grass biomass. This is a graph from an MSc student of our program showing disc pasture meter measurements from areas where rhino had been removed in red compared to areas where they hadn't in blue. And you can see that grass biomass increases once rhino is removed from the system. But apart from the removal, they're also suspected to be important in the creation and the maintenance of grazing lawns. So grazing lawns are these highly productive, highly preferred grazing grass species that consist of stoloniferous species. And these stoloniferous species are easily shaded out by tall grass species, but except that they do well under heavy grazing pressure. So under heavy grazing and continuous grazing, the sword shifts from a tall grass sword to a short grass sword. And rhino and hippo are believed to be primarily responsible for the creation of these lawns. But apart from just creating them, Waldron et al. In 2008 showed that they also might be important in the maintenance of existing lawns. And they showed that when you remove rhino from areas where that receives quite a bit of rainfall, then the grazing lawns that surround wallows start to disappear. But once you remove them from areas that is drier, like Imphalosi that's shown in the right panel, then it seems as though smaller species might be capable of taking over that role of rhino and maintaining the lawns in their absence. So the structural heterogeneity is also shown on a landscape scale. This is a study from Kruger showing that in areas where rhinos attain higher density, there are about 20 times more of these lawn patches than in areas with low density. But this is where the picture becomes a bit fuzzy. Clearly, there's some evidence that rhino maintain the structural heterogeneity, but to what extent would other species be able to compensate for this role of rhino? In 2016, Van der Plas and colleagues showed in HIP, they reported on a 10-year grazing exclosure experiment and showed that when you exclude rhino, but you include some smaller species or you allow access to them, then you don't see these structural differences in the grass layer, suggesting that they are compensating. But even if they are able to compensate, to what it's perhaps unlikely that they would be able to compensate everywhere. So this is a study on risk that we did in HIP, where we manipulated risk, and for 2 years we looked at which species eat where. And we showed that once if you have a safe area, then grazing impact is roughly equal between mega and meso grazers. But once the area becomes a risky area, then mega grazers are responsible for about 72% of the grazing pressure in these risky areas. So perhaps once we lose rhino, smaller things like impala are freed from competition and they have the opportunity to increase in abundance and take over this role. But there's actually a lot of evidence suggesting that rhino grazing are facilitating smaller grass species or smaller grazer species. And their creation of these lawns are actually creating a resource without which the system might not be able to maintain such high numbers of smaller species. But so whether smaller ungulates are increasing or decreasing, surely that's going to have cascading effects on the capacity of our parks to maintain healthy predator populations. Okay, so let's assume that rhinos do then influence the structure of the grass layer. Then they should have an indirect effect on fire patterns. So the low stature of grazing lawns ensure that it doesn't have the biomass to burn. So the distribution of these grazing lawns within the landscape should therefore influence fire intensity, fire frequency, and burn pattern. And there's one study that looked at this where they actually showed that once you remove rhino from the system in the gray bar, then the fire burns evenly across the landscape and it burns larger patches. In contrast, when you don't remove rhino in the black bars, fire burns smaller patches and the burn pattern afterwards is a lot more heterogeneous. And obviously, fire is a pretty influential player in savannas. It changes tree grass ratios and it changes tree composition. So through its effect on vegetation states, fire could also be influencing climate. And not just through carbon sequestration potential, but also by changing potential albedo. So albedo is the reflectance of the sun's energy from a particular surface. So shortly after burns, obviously, the absorption of the sunlight on the blackened surface is more. So that has a warming effect. But in the long term, because grass is more reflective than trees, if fire is shifting tree grass ratios towards grass, it should have an increase in albedo and a cooling effect. This is Linda Wieden's thesis, or she went out and quantified some of these differences between albedo, between grazing lawns, tall grassland, and woody encroached grassland. And she found quite significant and consistent differences between these grassland states, and showed that grazing lawns have a higher albedo, so a higher reflectance, compared to tall grass swords, and tall grass swords more reflective than woody encroached grassland. And she also showed that the more bare swell you have, the lower the albedo. So what this actually means for temperature, we're not actually sure. We don't know so much about this system at this point, but we do have a PhD student that would be starting soon looking at some of these issues. And another way in which rhino can disproportionately impact their environment is in the way that they move nutrients across the landscape. So there's been a lot of recent studies on animals animals moving nutrients from nutrient source to nutrient sink zones. And the idea is that they can move nutrients against abiotic accumulation gradients. So for example, if nutrients accumulate in bottomlands, but herbivores might be feeding preferentially in these bottomlands and then defecating and urinating upslope. So they move nutrients from areas of excess and deposit them in areas of deficit. And the idea is that megaherbivores should be particularly important in this regard because they have a longer gut retention time and they move over greater distances. So they should have the capacity to move nutrients further. But for rhino's not a particularly wide-ranging megaherbivore, but they do have a very peculiar way of moving nutrients across the landscape. So, and we know very little about what the consequences are of these massive nutrient inputs at middens. And rhinos might also be differing in terms of where they move the nutrients around. So this is where a study where we quantified dung density of different species in these contrasting habitat types. And we showed that if the habitat is relatively open and safe, that's where you have the mesoherbivore dung accumulating, whereas the megaherbivore dung tend to accumulate more in the risky areas, risky, dense, less visible areas. So for a plant that grows in these risky areas, they might actually depend on these large invulnerable species for fertilization. And body size doesn't only determine how much nutrients is returned by an animal where, but it might also change which nutrients are being returned. So it takes a lot of phosphorus to maintain structural tissues, such as bone. So phosphorus requirements should increase with body size. And it's been predicted that the nitrogen to phosphorus stoichiometric ratio or requirement in invertebrate consumers can range by as much as 24:1 in a 10-gram vertebrate compared to 9.6:1 in a 1,000-kilogram vertebrate. So if animals are eating the same food, then what is returned by a rhino might not actually be the same as what is returned by an impala, for example. And this is another MSc student of our program, Laura van Veenhuisen, and this graph shows fecal nitrogen to phosphorus ratios plotted against the log of body size. And you can see that it roughly follows prediction. So you have an increase in nitrogen to phosphorus ratio with an increase in body size. And the variation is probably, the variation within species is probably due to variation in original diet. But we know very little about this at this stage. This is an experiment that we have running at the moment where we want to see how these dung stoichiometric ratios, if it's actually translating into nutrient content differences within grass. But it's early days. I can't show you anything from this yet. Okay, so obviously if rhino is controlling all of these things, especially tree grass ratios, then they should be having an influence on the amount of carbon that a system can store. So how do these different rhino-maintained vegetation states differ in terms of their carbon storing potential? And at this stage, we have we don't really know what the answer is to this, but there's a PhD student starting with our program that will be looking at some of this. He will focus on how the loss of rhino, what that would mean for climate vegetation feedbacks. And one of his chapters will focus on carbon sequestration potential, and the other one on albedo, the long-term albedo that I mentioned before. And this is a long-term program, and hopefully we can get a lot of MSc students looking at some of these other gaps that I hope that I have highlighted. But there are many unknowns still when it comes to rhino's impact. For example, what is their role in seed dispersal? Which species are dependent on rhino for seed dispersal? Or how many co-extinctions are we to expect if we do lose rhino? So clearly, this picture of rhino and its impact is becoming pretty complex. And perhaps some of you would be even more convinced by this quote that I read out in the beginning. But I would like to finish off by saying that, by reiterating what I said in the beginning of the talk, that everything that we know about rhino is based on few studies done on relatively small scale. The rest is theoretical prediction and inference made from other species, sometimes completely unrelated species, sometimes even not even terrestrial species. So the point is this, we have, almost on every level, we have a good qualitative suspicion of what might happen. But we are very far from being able to predict this on a quantitative level. For some of these linkages, especially the indirect cascading ones, we're not even sure of the direction of the effect, much less the effect size. And at this point, I guess what I wanted to make clear with this presentation is firstly how pervasive the effects of rhino would be in the ecosystem, or the loss of rhino, but also how absolutely ill-prepared we are for facing these effects. And at this stage where the rates of rhino poaching at the moment, and the few places that we can confidently say they are still occurring at functional density, this should be, I think, a very disconcerting thought. It is our role to empower conservation managers with the ability to, oh, there's still 5 minutes, I've been speeding. Oh, okay, that's fine. It's our role to empower conservation managers with the ability to base their decisions on evidence. And at this stage, we have very little to offer when it comes to rhino. And the information that we are currently lacking will not only be useful in managing and anticipating the fallout from rhino extinction, but it would also be immensely useful in eventually designing our restoration strategies. So at the moment, we are very busy trying to save rhino, and I am obviously not criticizing that, but in addition to this, we need to start designing some forward-looking programs. We need to try and arm ourselves with the knowledge that we are going to need long before rhino actually go extinct. By the time that rhino populations start falling below functional density, which it probably already has in many places. And then this information can also start feeding into the restoration programs. So informing things like how do we decide on restoration priority sites, for example, or how do we account for uncertainty in our decision making. We are at the moment entering an era where conservation is increasingly embracing restoration. And just think of all the rewilding programs all over the world at the moment. And we have the opportunity to greatly contribute to this. But this opportunity might be closing faster than we would imagine. And we do need to act fast.